Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about reflow oven. So let's dive deep into it. So why do we need reflow oven? Well, reality is that we want mass production, and mass production needs efficiency. Every single stage in a chain of production defines how fast you can manufacture it. Meaning if you have let's say 10 steps and one step is taking too long, that simply means it's going to take too long to make it. So fundamentally, every single step has to become as efficient as possible. Now, through-hole components, they worked very well in the early 60s and 70s and 80s, but they reached a point where they are no longer fast enough, meaning through-hole components, you can buy it, you can put it, everything works. But here's the deal, they have very long legs, meaning you have to either buy pre-chopped of them, and that becomes an extra step that you have to do. And then not to mention, soldering them is also very tedious, and there is a penalty. The penalty is that you have to drill a hole in your PCB. Now, either you can drill a hole or stamp punch a hole, but holes are expensive. So if you have a PCB, especially let's say a keyboard PCB and all that, if you want the price to be low, you do not want holes in them. As little or as few holes as possible. People work their ass off to make sure that there is as little as possible holes in PCB. So holes are not desirable, and through hole components therefore not desirable. So once we have pick and place machines, SMD became the de facto standard. Now, okay, you have surface mounted device, you have a pick and place machine that is putting there. How the heck you gonna solder it? You're not gonna go there and like solder it. Be mindful, there are robots that do that, but those are for specialty components or very low throughput environment. You're not gonna mass produce like 100,000 of those. So there is some serious limitation. That's why we need something that can do things with very few steps, because we have every steps add cost to you. So you can be like, hey, what if I have this power supply and what if 90% of the components are non through hole PCB mounted and surface mounted, and then one is through hole. Yeah, you will be shocked how much price happens just because you added one step extra. So that will directly go to your customer. Now again, if your device is worthy enough, people will pay for it. If it's not, don't be shocked. So it takes a serious amount of engineering to reduce complexity of manufacturing. That's why we require something that can solder for us reliably. So we go into oven. Now oven is in simplest term, it's a chamber that is temperature controlled. Now, when you're talking about temperature control, it's not like a soldering iron where you just heat it up. It's a very controlled device. It's a very measured system because it has to follow what you call predefined temperature profile. Now, this part, temperature profile, that's the key here, because you many times could be putting the whole thing there. It has to be done in such a way that A, it does not overheat, B, it solders everything reliably. You cannot be like, okay, I sent it again, okay, now I have to resend it. No, it has to do everything in one go. So our engineering gave us this graph. Now be mindful, this graph will change in terms of its proportions depending on the tool that you're using, but this idea will remain the same. You will always have a profile. Now profile will come from your solder paste manufacturer. Whoever is manufacturing your solder paste, they will give you a profile. Now be very mindful of that profile. It's a starting point. It's never supposed to be your final thing. You take that profile, you test it on your actual equipment, actual thing that you're going to manufacture, and then you're going to fine tune it. You have a feedback loop to fine tune to increase yield and speed. So, and be mindful, many times you are sending the whole component, so it could not melt or warp any other components. So how do we achieve that? Well, first, you slow down, meaning you send your component, you slowly ramp the temperature. So even if you have the energy, electrical energy to just wabam it with as much energy as you need to, you do not do that. You ramp it up 1 to 3 degrees Celsius per second. You slowly ramp it up. You ramp it up to soak temperature. Generally, soak temperatures are around 150 degrees Celsius. So this could take few seconds to like slowly reach it up, and then you let it soak. Why do you let it soak? Because again, every component has a certain level of, they're not graphite blocks, let's just put it that way. They're not graphite blocks. So if you heat it up, it becomes equilibrium temperature inside. It takes time to heat up, and different things will heat differentially. So this re-soak temperature allows everything to reach up to a certain point where it's like, okay, you do not want something to be like barely expanding, other thing to be too much, because there are many things. There is copper, there is fiberglass, there is plastics, there is ceramics, there are a lot of other things in a PCB. So fundamentally, you have to make sure everything comes to the same sort of equilibrium. So this will be like 150 degrees Celsius from 60 seconds to 120 seconds. So you are talking about almost 2 minutes of soaking. So let everything soak. Then you are like, okay, now everything is done. Then you ramp this puppy up. Now ramping is also done gently. Everything here gently. 1 to 3 degrees Celsius, you ramp it up to around 217 degrees Celsius. This is where you get this puppy done. So once you ramp it up and then you cool it down. Again, you cool down slowly. You do not just run a jet to cool it down as quickly as possible or water cool it. Because again, you have to do 2 to 4 degrees Celsius of cool down. You do not want too little. You do not want too much. And because what will happen if you cool down too quickly? Well, these things will crack. Fundamentally, they will crack. So there has to be a very precise control of temperatures and ramp up and ramp down. That's why if you watch any system, there is like very serious engineering placed into the situation system where it's like, what if it's a cold weather, right? And you start to reach a point where this is getting, let's say, 5 degrees Celsius per second. Yeah, there will be a heater there. Auxiliary heater would come on to make sure that the ramp does not disappear. Now, this is just a graph. Be mindful, every paste will have a different graph, but this is the core logic of it. And you may pay attention that hot temperature is not that hot. Your soldering iron goes higher than that. Yeah, that's the benefit of this heat stoked stage and this soldering boss. They are designed in such a way that because everything is heated up, everything is relatively hot, it does not take too much oomph to melt it. So this also another has the benefit, because if you have to reach 400 degrees Celsius, you can't put any plastics there, like cheap plastic. There are plastic, there are peak materials that can handle that, but cheap plastic, ABS and all that, those will get destroyed. So fundamentally, that's how we do it. So it's not just a temperature control chamber, it's a temperature control chamber where we have control over ramp up and ramp down. And conveyor belts are used for long system. Basically, if you want to do mass production, this sort of a oven, it's good and all, but it's not going to be mass producible. So you generally have a giant conveyor belt that keeps sending it, and conveyor belt will literally be this long. Meaning entry, it will be from ambient temperature, slowly it will ramp up to soak temperature, slowly stay in the soak temperature, slowly go to reflow temperature, and then slowly comes out. And the other end, there will be fans and some heater just in case if you are working in an uncontrolled environment. So that's how the oven part works. That's what they have to do. So you generally use large conveyor belt system for large jobs. So what about the setup part of it? Well, that's the intent. Oven is the intent is the temperature. How do you get that? Well, generally ceramic infrared heaters are used. Why? Well, our atmosphere is very infrared inactive, meaning it does not give a damn about infrared. Like, wait a minute, then why we have glow? Yeah, it's a small percentage of carbon dioxide. Everything else is just like meh. So when you have a chamber and you want to heat the components, you do not want to go the long route where you're like, okay, I have a hot air gun that is heating the air and air is hitting the object, then slowly raising the temperature is very inefficient. So to make sure that you do it very efficiently, infrared allows you to, like, wherever the photons are falling, it's heating up. So it's very efficient in that regard. It passes through the atmosphere, but you also have some air circulation happening. So majority of energy directly goes into PCB. That's a very efficient system, and air circulation that is happening because you are not doing it in a vacuum. So you do have some circulation. Sorry about that. So once you have some circulation and all that, you generally try to keep the volume as small as possible. Even though you can make it very huge, you do not want to, because if you make it very huge, the inertia, the air inertia in there itself will be a very big hassle in order to heat it up and to cool it down. So you want it to be as small as possible. So generally, that's why you will see they are very skinny. And that's by design. So if you are mass producing same PCB, let's say this is the size of PCB and you are mass producing hundreds of millions of them, then you will have a scenario where the PCB, just there will be a slit in this oven system. There will not be any space. Now, again, companies do not manufacture a very tight equipment. They make a scale equipment and then they scale it down. So you generally try to make sure the volume is as tight as possible. Or if let's say your conveyor belt is huge, you will design the PCBs to be big enough where it can capture it. So you can have like multiple small PCBs. So you want the volume to be as tightly controlled as possible. You reduce it. You do not want like giant air room that you are heating it up and cooling it down. Wasteful. That would be very wasteful. And cooling fans are also used to keep the temperature under control, because you may be wondering how the heck you put things on the other side. Yeah, you make sure that part remains cold. That's why IR is generally preferable, because be mindful, once you solder something, it does take a bit more temperature to desolder it. So if you can shade it, like if I can put another PCB as a shade material or some structure. Sometimes glues are also used. So it's a whole another hassle process to make sure that you have components on both sides. And good engineering requirement is like make sure all the big heavy components are only on the one side. Other side you can have like lightweight components, so it's much easier for surface tension to do its job. Otherwise it may require jigs to hold it up, or may require some extra steps. Again, it's not that it can't be done, it just increases your cost. That's up to you. It's cost optimization versus size optimization. So volume needs to be as small as possible. Cooling fans are needed, and tunnel is the easiest way to ramp everything up, because again, you have a physical component moving through like yours, and here you see everything slowly has a different temperature. So based on the flow speed, you can control precisely. Oh, it's here ambient temperature. Okay, by the time it reaches this checkpoint, it has already reached to the 150 degrees Celsius. By from this to next checkpoint, it already at the soak temperature time, and after that reflow, and after that cooling. So that's how we do it. This is how factories do it. This is one thing that China has mastered. Like in China, like the same way you can buy a washing machine, you can just buy these things. They are really good at it, like good at it. And these are almost like half artisan machine. They are not just like, oh, this is how it works. Because be mindful, you are talking about something that is dealing with heat. You're talking about something that everything is different, where your copper is going to behave differently, your transformer is going to behave differently, MOSFET is going to behave differently, everything behaves differently. And somehow these things have to equalize all of them reliably and hundreds and thousands of times each time. So they are half black magic. So can you make this of your DIY? Actually, yes, because PCB manufacturing in last 5 to 10 years has become very cheap. From PCBWay to JSL PCB and many other European options also. You have the option to just get a quality PCB made quite quickly. However, that PCB part is a mass production equipment, but picking and placing, that's a very niche case. So even if the companies have pick and place, they require a human to go there and replace the reels and place the components. That's why the price of actually filling up your component, it would be like 500 rupees for your PCB, 5,000 in order to just get it populated with components. So generally we prefer not to do that. So pick and place, that's why it's expensive. Reflow services, they are very expensive. So DIY hobbyist community have figured out a very easy way that they take a IR based oven, and voila, oven, AC mains control, and a thermocouple. That's all you need. Now, what about the brains part of it? That is very simple, very easy, and community have worked their ass off to make amazing tools. Even in terms of basically how they are controlling the AC mains that goes into it. The earlier versions were trying with triacs. Now they have solid state relay. So they can do very good thermal control, and like you can follow all the graphs and all that. It's very good. Like you will be shocked how good these things have become. Meaning these are just a very small, not even few $100. Like it's $100 to $200, and if you have tedious enough, if you can like grind through things, you can make it at your home. Like they can tell you, oh, I bought this oven. This is how I amped it up, and voila, it just works. It's surprisingly good. Anybody can do it. And if you do not want to go the oven route, you can take the same core, place it into a hot plate, and get like a pseudo sort of chamber system. Again, a good starting point if you are tight on cash. But okay, oven system is like surprisingly how good people have made their own system to be. Because be mindful, at very low price, the components that you can buy, it's so bad that you like might as well have built it in the first place. And that's why this community grew so much. Like you can buy firmwares and all that. Be mindful. What the first thing most people do nowadays, they buy the cheap Chinese one and flash the firmware with the free one. So anyone nowadays, and electronics is one of those things where inherently you kind of know how to build everything. It's not like medical where a doctor does not know how to make a scalpel. It's a different. This is electronics. It's like you're supposed to know how to deal with this sort of thing. So you can actually build it quite efficiently. And if you can get like quality insulation, low cost. So DIY is a very good, viable option. So why not buy that option? Well, there's the problem. The cheap ones, not this big puppy one. This big puppy, that's like shut up, take money. They will have an individual that will come there. They will figure out your pace. They will like, there is a lot of ecosystem here. So in that puppy, shut up, take money, and everything is sorted. But when you're talking about cheap ones, like especially for schools, hobbyist, maker spaces, things of that nature, the results people have been doing, and be mindful, PCBs are becoming more and more cheap. So everybody's like, dude, it's a hassle to get those things work. It's not just like, I just like, it just works. It is like at the very early stage of 3D printing, where it's like you have to work with it in order to get anything out of it. So cheap ones are that bad. That's why DIY community has become such a good active system. So for many systems, where like I can actually pay for it, it's like you may not be better off by paying for it. You may think it's like, oh, I'm paying for it, it's gonna nah. More than enough people have learned this the hard way, that is like, nope. So that's up to you. For many scenarios, like just make it yourself, because people buy it and then it becomes the project itself. It's like, get the damn machine working. Like some machines actually ship to customers where they have paper tapes on hot elements. Yeah, it burns. So you have to understand. And the big ones that are like, shut up, take money and it will work, those things, again, they cost so much that only a factory or corporation or companies can handle it. And be mindful, many of them also require gas line, meaning they will require nitrogen gas purging. Like, why do you need nitrogen? Don't we have flux for that? Yes, but it's one of those things. You never want to rely on one component. It's like flux is holding oxygen back. No, you do not want oxygen there. Then you want to have flux there in order to, for any oxidation that have already occurred, to handle by flux. You always want like multiple lines of redundancy. So nitrogen is generally used to isolate this whole area from moisture and from oxygen. So and the tunnels are generally designed for mass production system. And if you do not do testing and proper tuning, you will have this, what we call tombstone. So if stencil is not perfectly cut and then the application is not perfectly done, you do not have the same amount of paste on both sides, you will literally have one will becoming a bit more high surface tension and it will just like yeet. So you will have yeeted component. It does happen. It's a very funny thing when you see it, but that's why you do need to what we call batch testing. Meaning if you buy this and you're like, okay, everything's sorted. No, that's not sorted. That's just step one. The graph charts and all that, that's step one. Then you will run, let's say you are making Raspberry Pis, you're gonna run at least 50-60 batches of them, and then you're like, okay, what is the yield rate, what is the common failure mode that in all those failures that have occurred. Then you study it, then you find it, then you do an alpha run, then you do mass production run. So it's a artistic kind of scenario. It's not something like, people who work with this, they're like, dude, it's way too much trial and error, like a lot of trial, and that's why they have machine visions and a lot of systems to actually check and verify, is it working or not. Because you would think like, oh, we are sorted, like we just place it, it works. Yeah, it's not that good. Not in mass production speed where you're like hundreds of boards going through per hour. We are not that there yet. Like we can do it, of course we are doing it. It's just like, it's not just like shut up, take money. It's not there yet. So that's why like it does take a lot of fine tuning and precision. And this is what China has mastered. Like if one thing that China has mastered in the last 40 years, this is it. They're good at it. Like they're good. So this was my presentation on basically Reflow oven. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.